theorem, we have following theorem. There is a covariant functor. There is a covariant functor from the category of chain complexes to the category of graded groups and homomorphisms. Graded groups and homomorphisms of degree 0. Which assigns to a chain complex, C its homology groups, group HC and to a chain map tau and to a chain map tau its induced homomorphism tau star. So this we have seen already. Already we have seen that if we take the chain complex, then we get its homology group, right? And if we take a chain map, then it is we get induced homomorphism from. And one can easily verify that all the properties for this assignment to be a functor, covariant functor, will be satisfied. Next. Now we define a homology on any given simplicial complex. KBA so simplicial homology. Simplicial homology. Let K be a simplicial complex. Let CQ K let CQ K be the abelian group be the abelian group uh, generated by the oriented Q simplices sigma Q with relation with relation 1Q plus equal to 0 if and sigma 2Q are are different oriented Q simplices corresponding to the same Q simplex Q. So basically, when we take a simple oriented Q simplex, right, sigma, right, then minus sigma means the same simplex with opposite orientation. And this is for all, this is for all Q. Now we define boundary map. Define this from CQ K to CQ minus 1 K per Q greater than equal to 1 by CQ boundary Q side over V naught V1 and so on V Q is equal to summation 0 less than equal to Q minus 1 to the power I V naught V1 VI have VI plus 1 VQ, where this V naught V1 VI cap, so we will use this notation. So here to write one note. This we'll use just this VQ. This denotes the oriented Q minus 1 simplex obtained by omitting VI, right? Basically, it is it represents if we put minus 1 to the power I with this, then this will represent oriented face of this simplex Q minus 1 dimensional face, right? This orientation induced from the orientation of this simplex. So, for example, this is if I take, for example, this V naught, V1, V2, then V naught, V1 cap, V2, it is what? It is simply, it is this V naught, comma V2, right? Putting cap over V1 means V1 has been thrown out, right? So if you throw out V1, what will you be left with? V0, V2, right? So this is basically this space, right? Now, so this is well defined. So recall that this is basically oriented simplex. So because this CQK, it is generated by the Q oriented Q simplices, right? So if we define this map, because we want it to be a homomorphism. So we can define it over over simplices, right? That is generator Q simplices, that is oriented Q simplices, that is generators of this QCQK, right? And it should respect the relation, right? So relation uh, here is basically sigma 1 q plus sigma 2 q equal to 0, where sigma 1 q and sigma 2 q are oriented simplices corresponding to same simplex, right? So given any simplex, it will have two orientations, right? So with each orientation, the simplex is called oriented simplex, right? So if we choose one orientation and then with that orientation, simplex is called an oriented simplex. If you choose other orientation, then with that orientation, simplex will be called oriented simplex, right? So every for every simplex, we will have two oriented simplexes corresponding to different orientations. So if this is there, then we'll have this. But if bound this is a homomorphism, then we have to have sigma boundary q sigma 1 q plus boundary q sigma 2 q equal to 0. We have to have this. If sigma this is a homomorphism, we have to have this. So we need to prove this actually. Also, we need to verify that this is well defined here, because for any oriented simplex, we can have many. So, for example, let me just call. Uh, yeah, for example, if I take this one. Then this V naught, V1, V2. So this, right? If we are considering oriented simplexes, right? So we can write this is same as we can shift it, right? So to V1, V0. Okay, it is V2, V0. This and this, they will be equal, right? Because they differ by an even permutation. Why? What you have done, you have considered, you have applied a permutation. 0 goes to 1, right? 2. This 0 goes to 1, 1 goes to 2, 2 goes to 0. So this is product of two transpositions, right? So basically, this is your event permutation, right? So yeah, so if you apply this over this one, you will get this. So these two will be same, right? See, these two will represent same oriented simplex. But if I just take V1, V0, V2, then this will not represent same oriented simplex as this one. Right? So these and this, they will be different because they differ by a transposition, right? That is this 0, 1, right? So V0 and V1, they are interchanged. So, so yeah, so given any oriented simplex, we can have more than one representative for that, because that is a class. So, what is guarantee that if you apply this boundary map over this and if you apply over this, they will be same. What is the guarantee? So that is the question. Now we will see that they will be same actually. So what we can do? Uh, uh, so if we have two representatives, right? So suppose we have sigma and sigma prime, right? And they represent same oriented simplex, right? It means what? It means that you can obtain sigma prime by applying even number of permutations. Yeah, by applying an even permutation, right? That is you will have some um, uh, so suppose you apply some a1 uh, sigma, then you can apply a2 a1 sigma, then like this, and then in the end you have some a some you can write er and so on a1 sigma, and you get this. R is even, right? So if your AIs are transpositions, we call they are permutations of this like this alpha beta, right? Now what if we can prove that, if uh, we prove that this boundary map applied over sigma is same as boundary map applied over uh, a 1 sigma, or I should write here a sigma, where a is a transposition. Okay, of this part. So if we can prove this, then you see whether you apply sigma q over this and this, it will be same. But then sigma q applied over this and this will be same, right? And so on. In the end, what will you have? Sigma q, sigma boundary map over this equal to boundary map over this. But then this and this, they differ only by the transposition. So boundary map over this and this will be same. Sorry, just a minute. Uh, will not be same actually. They differ by a negative sign. Right? So yes, so, minus. Okay. So this thing. So we will prove actually this, right? So minus because even number of times you have to do, so you will get ultimately equal. So this sigma boundary map over this equal to minus of boundary map over this, but boundary map over this will be minus of boundary map over this because they differ by a transposition, like this. So if you continue like this, then because this is R is even, so Sigma prime is obtained by applying even number of transpositions over sigma. Uh, means you will have that boundary map applied over sigma equal to boundary map applied over sigma prime. Now, how will you show this? First of all, now what you can do is every transposition you can write something like this. So what? Suppose that we have following transposition, right? And alpha is less than beta. Always you can write, right? Because then you can write beta alpha if that is not true. Now alpha beta, this you can always write like this. First, alpha plus 1, okay. Then you apply alpha plus 1, alpha plus 2, continue like this, and you continue, then you keep on increasing, then you will have uh, uh, then in the end you will have beta minus 1, beta minus 1, beta, so beta minus 1 comma beta, and then again you will apply this so this one will be your beta minus 2, beta minus 1, and you continue like this, and you will have alpha plus 1, like this. Right. All these every transposition alpha comma beta you can write like this. So this is basically this is your alpha plus 1, then alpha plus 1, alpha plus 2, like this, and then you continue. So I think this is the way we can write it. But if I write maybe more explicitly, alpha plus 1, alpha plus 1, alpha plus 2, then beta minus 2, beta minus 1, then beta minus 1, beta minus 2, beta minus 1, then you have alpha plus 1, alpha plus 2, then alpha plus 1, like this. I think so you can see that we have seen that for every alpha beta you can write as some transpositions here, and then one transposition here, and then some transpositions here. So basically, this is your this is basically inverse of this one. Okay, uh, and the transpositions here, they are of this nature, uh, a plus 1, and this also is of this form. So again, this is an even permutation, right? Because number of transpositions here and number of transpositions here is same. So even, and then this one odd. So now, if you if sigma and sigma prime differ by a transposition of this form, right? So suppose sigma prime equal to a plus 1 sigma, or more specifically, we can write I plus 1, right? I goes, so, right? So this basically can write V naught Vi plus 1 Vi, and then others are unchanged. So this is sigma prime, right? And sigma is just V naught V1 VQ, right? So if you just interchange I times Vi and Vi plus 1, that is, you apply this permutation over this, then you get this one. So we will show that this boundary map, this prime equal to minus of boundary sigma, right? So this is easy. This is easy. So if we can do this, then we'll be done, because uh, uh, these will be this and this. They will cancel each other, and then this will give you one negative sign, right? So we'll be done. So if I apply boundary Q, plus 1 Vi VQ, this is by definition minus j equal to 0 to q, right? Minus 1 to the power j b naught some so here So this is simple actually. This if j is less than this j is less than I, right? That is Vj is in this side of Bi plus 1. Then whatever faces we are getting, uh, uh, so we have to write actually to 3. So j is less than I. Bi q, bq, okay, uh, and this is from 0 to I minus 1, then uh, you have minus 1 to the power I, you have b0, b I minus 1, the I plus 1 will be thrown out, then we have vi, and then q, then again minus 1 to the power I plus 1, we have b0 and I plus 1, then vi will be thrown out, and then q, like so, plus, then uh, summation j equal to I plus 2 to q minus 1 to the power j v naught vi plus 1 vi, and then vj vq, something like this. If you carefully see this, then you'll find that this is the minus of q v naught v1 vi vi plus 1. Uh, so a similar idea we can use to prove that this sigma 1 q plus q equal to 0. Similar idea we can use. Uh, Now, this boundary map, this is well defined. We have defined a homomorphism from CQK to CQ minus 1 K, right? Now we want to show that this is actually a differential over this graded group. So for that, basically we want to show that the CQK with these boundary maps, they are chain complexes. So what we have to show is we have following plane, right? So let us prove it. Q minus 1, Q, if we apply Q, then by definition, this is minus 1 I 0 to Q Q, right? Ith vertex has been thrown out. This, if I again apply this one over this, then we'll have this double summation. This plus here, if your j is greater than I, then because this vertex is removed, so everything will shift one place back. So if I remove uh, V naught, Vi, if I remove Bj here, so Bj is not exactly at this jth place, but it is j minus 1th place, it's j minus 1th place. So here sign minus 1 power j minus 1 will be here. Now, if we interchange the role of I and j here, right? By interchanging the role of I and j in the second summation, we get negative of the first summation. So you just see that because this is just j and I, they are just simply symbols, right? So in this summation, if I change role of j and interchange role of j and I, then here what we have I less than j, right? Sorry, just yeah. So here we'll have I greater than j. Right? We have I. Now here we have j will be there, I will be there, right? And then here, but this sign, of course, this sign we will keep as it is. Okay. So this here it is minus 1 to the power j is there. Here minus 1 to the power j minus 1 is there. So minus sign, there is difference of minus sign between the two. So they will cancel actually. So we will have actually 0. That is this is true.